Okay, as the last item in this chapter, I will try to explain how we see rainbow colors on the soap bubble. Okay, and in order to explain it, there's one thing I have to mention first. Okay, let's go back to the spring semester and take a look at what we have learned in the chapter 15. There we learned what will happen if we send a mechanical wave along this wire or the rope, which is connected to the surface of the wall. And there were two examples. On the left side, this rope is fixed on the surface of the wall, while on the right side here, this string or this rope is not fixed, but it can easily move up and down like this. So then what will happen if you send the pulse, which looks like this, to the other end of the rope? We learned that in this case, now this end cannot move, so it cannot move up. So therefore, following the Newton's third law of motion, which is also called the action and reaction, the force applied to the wall will be given back into this string or the rope, so that when the pulse is coming back, it will be upside down. Okay, this is what we learned. And mathematically, it is equivalent to saying that the phase will be shifted by pi or half lambda when it's coming back, or reflected off a fixed end. And fixed end is just like hard surface. Okay, and in this case, now it's not fixed, so therefore Newton's third law doesn't have to work. So the pulse will come back as it is without phase shift. This was the case of the reflection of a free end or soft surface. Okay, so why do I mention this? Very similar thing will happen when light waves get reflected from a surface. And then of course, how does a light wave can be fixed like this? Of course, it is not fixed. Actually, as I said, the left side is like hard surface, on the right side is like a soft surface. For light, hard surface is the surface going into the medium of the higher refractive index, and soft surface is like going into the medium of the here lower refractive index. Okay, so here in this case, okay, N2, this part is higher and this part is lower, and here this part has a lower refractive index and this part has a higher refractive index. Okay, so what it means is that when light goes into the hard surface of the higher refractive index, it will be shifted by pi and it will come back like this. But in contrast, when it is reflected off the softer surface of the lower refractive index, then it will be reflected off without phase shift and it will come back like this. Okay, this will be used in the next slide. So now let's try to understand how we see these beautiful colors on the surface of the soap bubble or on the surface of the rainy street when the car has left. Okay, so this is certainly an interference color, and it is also called the iridescent color. So it is an interference phenomena, and it actually involves a reflection of the thin film. And by thin film, what we mean is that in this case, it will be the very thin layer of soapy water, and in this case, it will be the very thin layer of gasoline. Okay, so anyway, what is happening is the interference between two light waves. And where are the two light waves? How do we have two? Okay, let's try to expand, for example, this part, zoom in and see what is going on. So it will basically look like this. So the first layer is air outside, and second layer will be the thin film. Okay, and then the third layer will be another medium on the other side of the thin film. So for example, in the soap bubble case, this will be the air inside, and in the this example, the third layer will be the surface of the street, just like asphalt or concrete. Okay, so in this case, the light will originate from outside, so it will come in from the air. First, you will see the surface of the thin film and then get reflected. Okay, and then part of the light will go through and travel this much, and then see the second surface and then get reflected. So when they come out, what we see is the interference between these two reflected light waves. Okay, and what we learned from the previous slide is that when the light gets reflected from the surface of the higher refractive index, it will be shifted by half lambda. Okay, so then typically the outside is air, which has the lowest index of refraction. So therefore, when it's reflected off the thin film, typically thin film will have higher refractive index, so therefore there will be a pi shift. But then how about the reflection of the second surface? Now we have to compare between N2 and N3 and see which one is higher. Okay, now let's first think about the situation of this gasoline layer on the surface of the street. Here the third layer, which is asphalt for example, has a very dark color, which means that the refractive index is effectively much higher on the third surface. Then there will be also a pi shift from the inner surface of the thin film, so that in this case there will be pi shift for both reflections, so therefore eventually their effect will cancel each other. So we don't have to consider the pi shift in this case, and the only thing we have to consider is the total path difference. So the first wave is reflected here, and second wave travels in and gets reflected, so therefore twice the thickness of this thin film will be the path difference, which is 2L. Okay, so if this is integer multiple of the wavelengths, that will be the constructive interference condition. Okay, here, but we have to consider one thing. We learned that the wavelengths inside the medium depends on the wavelengths, and this is happening inside this matter, which has the refractive index N2. So therefore the wavelengths in this case is not the original wavelengths, but the original wavelengths divided by the index of refraction. So therefore it has to be lambda divided by N2. Okay, and another thing we have to consider is that this M, it is an integer, but it cannot be 0, because if it is 0, then it means that there will be no thin film. So therefore it has to start from 1. Okay, so finally we can summarize that the constructive interference condition, which means there will be a bright light, we can say the condition is 2L is equal to M multiplied by lambda divided by N2. Okay, and then how do we see different colors here and there? Actually, it actually means that their thickness may be different, because different color means different wavelengths. So therefore when wavelength is long, then it will require a thicker thin film in order to satisfy the constructive interference condition. Okay, and then now let's think about the case of soap bubble. Now in this case N2 is larger than N1, and it is also larger than N3. So in this case pi shift will occur only on the outer surface, and there will be no pi shift inside. So therefore when you consider only the path difference, which is 2L, and if it matches the integer multiple of the wavelengths, then it will have pi shift. So therefore there will actually be the destructive interference. So in order to recover the condition for the constructive interference in this case, you have to add one more pi shift, which is half here. So now this condition and that condition look different, because in this case there were a pi shift on both surfaces, and in this case there was a pi shift on only one surface. Okay, so important thing is that you have to think about which layer has a higher refractive index, and then depending on how many times the pi shift occurs, you have to compensate for it if necessary. Okay. Okay, let's finally make a summary of this chapter. Today we have learned many things, right? Okay, we first learned the Huygens principle for waves. So it was good for not just for light, but it was good for any waves. And using this Huygens principle, we learned the Snell's law of refraction, And before doing that, we actually discussed the concept of the refractive index, which was the indication of the slowing down of the light in the medium. Okay, and we also learned the law of reflection, which always tells us that the angle of reflection is equal to the angle of incidence. And actually, by using this Snell's law of refraction, we learned that there is a phenomenon called the total internal reflection. So this happens when the light wants to travel from the medium of the higher refractive index into the lower refractive index. So all the light may get reflected off when the incident angle is larger than the critical angle. Okay, and we also learned that the diffraction and interference are the two most important properties of waves. So we can use these methods to prove the wave nature of light. And as the most important example of the interference experiment, we study the result of the Young's double slit experiment. Okay, we also learned the interference of light from thin films. Okay, and in the next lecture, we will continue to study these interference and diffraction and think about many different examples like listed here. Okay. Anyway, it was a long lecture, but I hope if you have any questions, then please don't hesitate to ask questions in the classroom. So I will be happy to take any questions. Okay, see you on Thursday in the classroom. Goodbye.